Imagine fast-forwarding the universe. Galaxies drift apart in slow, inevitable motions. Stars fade one by one as their fuel runs out. The night sky empties, its bright clusters dissolving into cold, silent space. Black holes dominate everything that remains, swallowing the last remnants of matter before shrinking into nothing through evaporation. Temperatures fall closer and closer to absolute zero. Over time spans so immense, they dwarf the age of the universe 1 trillion times over. Everything we know slowly unwinds. Scientists can't watch these events play out directly, but the physical laws that govern the cosmos allow them to calculate when each transformation will occur. But before exploring how the universe truly ends, we need a complete picture of the path it takes to get there. If you're ready to follow the universe's timeline from now to its final moments, subscribe now. Each stage reveals a new clue about how everything we know moves toward its ultimate end. The starting point is the universe we inhabit right now. Precise measurements from the European Space Agency's Planck mission determined the age of the universe to be 13.8 billion years by analyzing the cosmic microwave background. This faint radiation, with a temperature of 2.7255 Kelvin, is the leftover heat from the early universe. It appears almost perfectly uniform across the sky, with tiny fluctuations only millionths of a degree above or below the average. These patterns are extremely important. They reveal how matter was distributed shortly after the Big Bang, and that distribution shaped where galaxies formed, how massive they became, and how structures evolved over cosmic time. The expansion of the universe is another critical factor that shapes its future. The Hubble constant, which measures how fast galaxies are receding from one another, currently falls between 67.4 km/s MPC, which is measured by the Planck team, and 73 km/s MPC, measured by the SH0-ES collaboration. This disagreement is known as the Hubble tension. The driving force behind the observed acceleration is dark energy. Though incredibly small in density 6.91 times 10 to the power of negative 30 grams per cubic centimeter, it fills all of space. And unlike ordinary matter, its density does not decrease as the universe expands. More space means more dark energy, increasing its relative dominance over time. With these measured conditions, cosmologists divide the universe's future into several major eras. We currently live in the stelliferous era, the era dominated by stars. This period began roughly 100 million years after the Big Bang, when the first stars, massive, short-lived, and incredibly luminous, burst into existence. Since then, star formation has climbed, peaked, and started to decline. Around 10 billion years ago, the universe reached its peak star-forming activity, producing stars at about 10 times the current rate. The Milky Way, during its peak period, created 5 to 10 solar masses of stars per year. Today, that number has fallen to around 1-2 solar masses annually. Observations of galaxies like M82, the Large Magellanic Cloud, and Andromeda show similar downward trends. Galaxies are depleting their reservoirs of cold molecular gas, reducing their capacity to form new stars over time. The stelliferous era is expected to continue until roughly 100 trillion years in the future. By that time, galaxies will have used up or expelled nearly all of the gas required to form new stars. The only remaining stars will be long-lived red dwarfs, with masses between 0.08 and 0.6 solar masses. These stars burn hydrogen at very slow rates. A red dwarf with 0.1 solar masses has an estimated lifespan of 10 trillion years, far exceeding that of the Sunday. Red dwarfs constitute the majority of stellar populations, and they gradually decrease in luminosity as their hydrogen supply is consumed. With no new stars forming, the universe transitions into the degenerate era, named for the stellar remnants that dominate this period. White dwarfs, neutron stars, brown dwarfs, and black holes become the primary inhabitants of the cosmos. White dwarfs, initially blazing at temperatures above 100,000 Kelvin, cool slowly over trillions or even quadrillions of years. Neutron stars, which begin at temperatures above 1 million Kelvin, gradually cool through neutrino emission and surface radiation. Brown dwarfs, which never reach the temperatures required for sustained nuclear fusion, cool steadily from their initial temperatures of 1,000 to 3,000 Kelvin to just a few Kelvin over extremely long timescales. Galaxies continue to undergo major changes during this era. Within the next 4-5 billion years, the Milky Way and the Andromeda Galaxy will collide and merge. Andromeda is moving toward the Milky Way at about 110 kilometers per second, and when the merger occurs, the galaxy's stars will largely pass by one another without direct collisions due to the enormous distances between them. However, their gravitational fields will distort and reorganize both systems into a single massive elliptical galaxy, often called Milkdromeda or Milkomeda. The local group, including the Triangulum Galaxy and more than 50 dwarf galaxies, will eventually merge into this larger structure as well. Beyond the local group, galaxies outside gravitationally bound regions will move beyond the cosmic horizon as dark energy accelerates expansion. Within about 100 billion years, even massive nearby structures such as the Virgo cluster, located roughly 53 million light-years away, will no longer be observable from the local group. These galaxies continue to exist, but their light cannot reach observers due to the expansion of space. Inside the merged local group, long-term gravitational interactions slowly scatter stars across large distances. Over timescales between 10 to the power of 17 and 10 to the power of 19 years, stars and stellar remnants undergo close gravitational encounters. These interactions can give stars enough velocity to escape their host galaxy entirely. Today, a star would need to travel at roughly 550 kilometers per second to leave the Milky Way's gravitational pull. Simulations of galactic evolution involving millions of stars show that most stellar objects will eventually gain enough momentum to escape, leaving behind only a small number of remnants tightly bound to the galactic core. Escaping stars will move through intergalactic space with minimal interaction. The stability of baryonic matter itself becomes a major factor in the far future. Some grand unified theories predict that protons, the building blocks of atoms, may decay with half-lives between 10 to the power of 34 and 10 to the power of 36 years. If proton decay occurs, atoms, planets, and stellar remnants would gradually disintegrate into lighter particles. Experiments such as Super Cameo Candae have set lower limits on proton stability, showing that if protons decay, their half-life must be at least 1.6 times 10 to the power of 34 years. If protons do not decay, baryonic matter can remain, although individual structures may cool and move apart over time due to gravitational effects. Black holes dominate the next enormous span of cosmic time. Today, black holes form through both stellar death and galactic mergers, and they are among the most stable structures in the universe. Their lifespans are determined by Hawking radiation, a quantum process through which black holes emit particles and lose mass. A black hole with 10 solar masses will take roughly 10 to the power of 64 years to evaporate. The supermassive black hole at the center of the Milky Way, Sagittarius A, with a mass of 4.1 million solar masses, will last around 10 to the power of 87 years. Even more massive black holes, such as the one in TON 618, estimated at 66 billion solar masses, may survive for nearly 10 to the power of 100 years. These estimates indicate that black holes persist for extremely long periods compared with stars and other cosmic structures. Meanwhile, the cosmic microwave background continues to cool. its temperature decreases by roughly 10 to the power of negative 10 Kelvin per year. Within 1 trillion years, it will fall below 0.0001 Kelvin, and far beyond that, it will drop below 10 to the power of negative 30 Kelvin, approaching thermodynamic uniformity. This cooling reduces the energy of photons, neutrinos, and remaining particles over extremely long timescales. When the last stars burn out, star formation in the universe is slowing as reservoirs of cold molecular hydrogen gas within galaxies are depleted. Observations indicate that the Milky Way now forms roughly 1-2 solar masses annually. Smaller galaxies, like the Large Magellanic Cloud, follow similar trends, and many dwarf galaxies have already exhausted their gas supplies. Red dwarfs, the smallest and most numerous stars in the universe, dominate this final stellar generation. Comprising 70–80% of all stars, they range from 0.08 to 0.6 solar masses and burn hydrogen slowly and efficiently. Unlike massive stars, which exhaust their fuel in millions of years, low-mass red dwarfs can shine steadily for trillions of years. For instance, a 0.1 solar mass red dwarf is projected to live for roughly 10 trillion years, far longer than the Sun's 10 billion year lifespan. These stars are faint up to 10,000 times less luminous than the Sunday. Systems such as TRAPPIST-1, 0.089 solar mass red dwarf, hosting 7 Earth-sized planets, illustrate the types of star-planet arrangements that will exist in the far future. As larger stars reach the end of their lifespans, they evolve into white dwarfs, neutron stars, or black holes, but red dwarfs continue fusing hydrogen in their cores. Even during this period, their luminosity gradually declines. Detailed stellar models indicate that a low-mass red dwarf will slowly increase in temperature in its core while outer layers adjust, causing a slight increase in brightness, followed by a steady dimming over billions to trillions of years. The cooling process for stars as they exhaust fuel varies depending on mass. Stars, similar to the Sun, after leaving the main sequence, expand into red giants, shed their outer layers, and leave behind white dwarfs that no longer sustain fusion. But the final generation red dwarfs are different. Most will never enter a red giant phase. Their core temperatures remain too low for helium fusion, and they simply contract slightly over time while radiating away their energy. In addition to individual stars, the composition and structure of star clusters influence the fading of cosmic light. Globular clusters, which contain hundreds of thousands of stars bound by gravity, can survive long after star formation stops elsewhere. Within these clusters, most stars are low-mass red dwarfs. Over trillions of years, these clusters gradually lose stars due to gravitational interactions. Open clusters, by contrast, are less tightly bound and disperse more quickly, contributing only briefly to the overall luminosity during this period. During this epoch, the total luminosity of the universe declines dramatically. At present, the combined starlight of all galaxies produces a background light density of roughly 2 × 10 to the power of -6 watts per square meter per steradian. As red dwarfs become the dominant population and the last massive stars vanish, this value decreases by orders of magnitude. By the time star formation has completely ceased, the observable luminosity of the universe may fall below 10 to the power of -9 watts per square meter per steradian. Infrared emission from red dwarfs remains the primary source of detectable radiation, primarily in wavelengths between 0.7 and 2 micrometers. Planets orbiting these stars will experience correspondingly dim skies. Systems like TRAPPIST-1 may retain habitable conditions for tens to hundreds of billions of years, thanks to the stability of their host stars' fusion. However, as red dwarfs age, their brightness fluctuates, sometimes dramatically. Stellar flares, magnetic activity, and slow changes in luminosity may affect any remaining biospheres, although the frequency and intensity of such activity generally decline with age. As star formation ceases, the observable luminosity of galaxies declines. Red dwarfs and white dwarfs remain as the primary luminous objects. The Milky Way and other galaxies no longer form new stars, and external galaxies will eventually move beyond observational reach due to cosmic expansion. The remaining detectable light will originate from long-lived stellar remnants. The timing of these processes depends heavily on star formation rates and gas depletion. Current models suggest that within roughly 100 trillion years, all star-forming regions in the universe will be exhausted. By then, nearly every remaining luminous object will be either a low-mass red dwarf or a white dwarf cooling toward invisibility. Even before reaching complete darkness, galaxies will be largely passive, with only a handful of faint red dwarfs contributing energy to the cosmic background. This timeline is based on measurable properties of stars, observed gas reserves in galaxies, and extrapolation of stellar evolution models developed over decades. Interestingly, the chemical composition of these last stars affects their lifespans. Stars with slightly higher metallicity, higher abundance of elements, heavier than helium, tend to burn slightly faster due to more efficient energy transport within their cores. Observations indicate that many red dwarfs in older stellar populations have metallicities around Fe divided by H equals negative 0.5 to negative 1, meaning they contain roughly 30–50% of the Sun's metal abundance. These stars, while long-lived, will fade slightly earlier than lower metallicity counterparts. Extremely metal-poor red dwarfs may persist longer than higher metallicity stars. During the later phases of stellar activity, ultraviolet and visible light emission from massive stars disappears, leaving the infrared as the dominant wavelength. Cosmic background radiation from stellar sources is primarily from red dwarfs, white dwarfs, and brown dwarfs. Even without ongoing star formation, interactions between stellar remnants such as tidal interactions, rare mergers, or gravitational encounters produce occasional bursts of energy, although these are far less frequent than during periods of active star formation. Red dwarfs have lifespans stretching trillions of years. The Sun will become a white dwarf hundreds of billions of years before the final red dwarfs exhaust their hydrogen. Systems such as Proxima Centauri and TRAPPIST-1 provide examples of low-mass stars that remain luminous for extended periods. After red dwarfs exhaust their hydrogen, star formation ceases due to the lack of cold gas and absence of massive stars. Remaining luminous objects are limited to stellar remnants. The transition occurs over trillions of years based on stellar lifetimes and gas depletion models. The cessation of star formation and the cooling of red dwarfs result in a universe where remaining luminous objects are primarily low-mass stars and stellar remnants. These changes are measurable and predictable based on stellar evolution models, observed gas reserves, and data from stellar populations across galaxies. The era of dark degenerate matter. After the last stars exhaust their fuel, the universe enters an era dominated by stellar remnants, white dwarfs, neutron stars, and brown dwarfs. Red dwarfs continue fusing hydrogen for trillions of years, while the majority of stellar populations have ceased fusion. Evolution is governed primarily by gravity and residual heat, with new energy sources largely absent. Cooling is slow, and interactions between objects are infrequent. White dwarfs are the most common degenerate remnants. These stellar cores, formed from stars with initial masses below roughly 8 solar masses, have no ongoing nuclear fusion. Instead, their pressure support comes from electron degeneracy, a quantum mechanical phenomenon that prevents collapse. Typical white dwarfs have masses near 0.6 solar masses and radii comparable to Earth's, making them incredibly dense, about 10 to the power of 6 grams per cubic centimeter. Their cooling is extremely gradual. Observations of the oldest known white dwarfs in the Milky Way, such as WD 0346 plus 246, reveal surface temperatures around 3,900 Kelvin, despite ages approaching 12–13 billion years. Models suggest that over the next 10 to the power of 14 to 10 to the power of 15 years, most white dwarfs will cool to below 5 Kelvin, radiating residual heat into the expanding universe. Some white dwarfs undergo crystallization in their carbon-oxygen cores. This phase transition releases latent heat, temporarily slowing cooling. Crystallization begins when the core temperature falls below approximately 10 to the power of 7 Kelvin, a condition predicted for white dwarfs older than several trillion years. The process forms a rigid lattice structure in the interior, while the outer layers remain gaseous, altering the star's internal structure over long timescales. Neutron stars, formed from more massive progenitors, dominate a smaller fraction of the degenerate population, but exhibit extreme densities on the order of 10 to the power of 17 kilograms per cubic meter, rivaling atomic nuclei. Born with temperatures exceeding 10 to the power of 11 Kelvin, they rapidly cool through neutrino emission in the first million years. Afterward, their thermal radiation diminishes steadily, approaching near absolute zero over quadrillions of years. Some neutron stars rotate at incredible rates, known as millisecond pulsars, reaching rotational frequencies up to 700 revolutions per second. Though their spins gradually slow due to magnetic braking, they persist as detectable, albeit faint, remnants in the long-term universe. Brown dwarfs, often called failed stars, bridge the gap between planets and true stars. With masses between 13 and 80 Jupiter masses, they never sustain hydrogen fusion. They initially radiate gravitational contraction energy and deuterium fusion for a short period, then cool to temperatures of a few hundred Kelvin within the first billion years. In the degenerate era, brown dwarfs continue to cool slowly, emitting faint infrared radiation. Objects like Y0855900714, one of the coldest known brown dwarfs at roughly 250 Kelvin, exemplify the conditions of billions of brown dwarfs across the universe. Collectively, these objects constitute a large fraction of baryonic matter still present outside black holes. White dwarfs in dense environments, such as globular clusters, can occasionally collide, forming more massive white dwarfs that may briefly reignite fusion or collapse into neutron stars. Neutron star binaries, though rare, continue to emit gravitational waves, slowly spiraling inward over trillions of years. These interactions are infrequent but represent the remaining high-energy events after stellar ignition has ceased. Brown dwarfs, scattered through interstellar space, may occasionally encounter other objects, forming temporary binary systems or ejected planets orbiting them, though collisions remain extremely unlikely due to vast interstellar distances. The luminosity of the universe in this era is dominated almost entirely by the faint infrared emissions of cooling white dwarfs and brown dwarfs. By 100 trillion years, the cumulative starlight of degenerate objects becomes negligible compared to the early universe. Energy fluxes from these objects are on the order of 10 to the power of -9 to 10 to the power of -12 watts per square meter, insufficient to sustain any large-scale processes or significant chemical activity. Over these long timescales, white dwarfs cool, crystallize, and radiate their remaining energy. Neutron stars continue emitting low-energy neutrinos, and some millisecond pulsars produce weak radio waves detectable only with highly sensitive instruments. Brown dwarfs eventually cool to temperatures below 10 Kelvin, approaching the temperature of the surrounding interstellar medium. Over 10 to the power of 17 to 10 to the power of 19 years, two-body encounters between degenerate stars and other remnants cause ejections from clusters and galaxies. White dwarfs, neutron stars, and brown dwarfs may be flung into intergalactic space. Galactic cores gradually lose mass. Simulations indicate that most remnants eventually occupy the outskirts of galaxies or drift alone in intergalactic space, with only a small fraction remaining in dense clusters. A typical white dwarf loses about 10 to the power of negative 30 watts per kilogram after trillions of years, radiating extremely low-energy photons. Brown dwarfs and the coldest neutron stars contribute similarly negligible power. Thermodynamic gradients diminish over long timescales, while physical laws continue to govern residual motion of degenerate matter, gravitational scattering, and subtle radiation of heat. The distribution of degenerate objects varies according to original stellar populations. In the Milky Way, simulations suggest roughly 90% of baryonic matter, not in black holes, will exist as white dwarfs by 10 to the power of 14 years, with neutron stars around 1% and brown dwarfs comprising the remainder. Other galaxies, depending on mass and star formation history, show similar patterns. Dwarf galaxies and satellite systems, often gas-poor, contribute primarily to cold white dwarfs and brown dwarfs, while larger galaxies retain denser clusters of remnants in their cores. Close encounters between two white dwarfs of sufficient mass can produce a Type Ia supernova during the degenerate era, with a frequency estimated at roughly 1 per 10 to the power of 12 to 10 to the power of 13 years per cubic parsec. Similarly, binary neutron stars may merge, producing brief gravitational and electromagnetic signals. These processes, though infrequent, occur during the period before black holes dominate the cosmic landscape. Entropy increases steadily during this era. As stars cool and energy is radiated away, free energy becomes increasingly limited. Over timescales beyond 10 to the power of 17 years, most objects will have radiated nearly all thermal energy, leaving cold, dispersed remnants. While white dwarfs and neutron stars are supported by quantum degeneracy, baryonic matter itself may eventually decay. Grand unified theories predict that protons might have half-lives of 10 to the power of 34, 10 to the power of 36 years, potentially causing degenerate matter to dissolve into subatomic particles and radiation. This period precedes the stage in which black holes dominate the universe, black dwarf transformations. As the era of dark degenerate matter unfolds, white dwarfs gradually cool and fade, heralding the emergence of the universe's next silent epoch. This is the era of black dwarfs, stellar remnants that no longer radiate visible or infrared light in any significant quantity. While no black dwarfs exist yet, because even the oldest white dwarfs in the Milky Way are only about 12–13 billion years old, their eventual formation is inevitable. Over timescales of 10 to the power of 14 to 10 to the power of 15 years, the last white dwarfs will reach temperatures of a few Kelvin, effectively becoming cold, inert spheres drifting silently through the cosmos. These objects represent the ultimate endpoint of stars, not massive enough to form neutron stars or black holes, and mark the universe's slow but inexorable march toward near-total darkness. The transformation from white dwarf to black dwarf is more than just cooling. As temperatures drop, the cores of white dwarfs, composed primarily of carbon and oxygen, begin to crystallize. This crystallization process is a form of solidification in which ions arranged into a highly ordered lattice structure. Laboratory studies of extreme density carbon-oxygen mixtures, combined with advanced stellar modeling, suggest that crystallization starts when core temperatures fall below approximately 10 to the power of 7 Kelvin. The process releases latent heat, temporarily slowing the cooling of the star and producing subtle shifts in the star's radius and luminosity. Over trillions of years, the core becomes a crystalline mass comparable in structure to diamond on Earth, though orders of magnitude larger and denser. Some particularly massive white dwarfs, approaching 1.2 solar masses, crystallize faster than their lower mass counterparts, altering internal pressure distributions and the thermal evolution of the remnant. As black dwarfs form, their outer layers cool to fractions of a Kelvin above absolute zero. Theoretical cooling curves indicate that after 10 to the power of 15 years, most black dwarfs will have surface temperatures below 5 Kelvin, emitting almost no detectable photons. Luminosities approach 10 to the power of negative 31 watts, making them hundreds of times dimmer than the faintest observable white dwarfs today, which emit about 10 to the power of negative 28 watts. In black dwarfs, the core is crystallized, while electron-degenerate gas in the outer layers continues to exert pressure, preventing gravitational collapse. Quantum tunneling may trigger nuclear fusion in isolated carbon nuclei at extremely low rates, producing infinitesimal energy bursts. These reactions gradually decline as the black dwarf cools, leaving the object effectively inert over extremely long timescales. Approximately 90% of stars are low-mass or intermediate-mass stars, so most stellar remnants will crystallize into black dwarfs. Galaxies like the Milky Way, Andromeda, and Triangulum may host hundreds of billions of these objects. Some remain gravitationally bound in galactic halos or globular clusters, while others may be ejected by two-body interactions, moving through intergalactic space. Black dwarfs will constitute a significant fraction of baryonic matter for extremely long timescales. As black dwarfs cool and mass distributions stabilize, interactions with nearby remnants and dark matter halos continue to influence stellar orbits. Simulations suggest that over 10 to the power of 17 to 10 to the power of 19 years, many black dwarfs will drift toward galactic outskirts or be ejected into intergalactic space due to gravitational scattering. In galaxy clusters, dense regions may retain some black dwarfs bound together, migrating toward cluster centers as energy redistributes. The majority of black dwarfs contribute primarily gravitational influence rather than energy output. Black dwarfs may capture nearby objects, forming temporary systems with planets or rogue asteroids. Some may encounter neighboring black dwarfs in dense clusters, potentially merging over extremely long timescales. These mergers release gravitational energy, slightly increasing the thermal energy of the merged object. The rate of such events is approximately 1 per 10 to the power of 14 to 10 to the power of 16 years per cubic parsec. Black dwarfs may undergo long-term changes due to weak subatomic interactions. Over timescales approaching 10 to the power of 34 years, proton decay, if it occurs, could erode nuclei within black dwarfs. Experiments like Super Kamiokande constrain the proton half-life to be greater than 1.6 times 10 to the power of 34 years. If proton decay occurs, black dwarfs may disintegrate over quadrillions of years. If protons are stable, black dwarfs could persist beyond 10 to the power of 15 years without significant mass loss. Most black dwarfs have carbon-oxygen cores, but higher mass progenitors can leave neon, magnesium, or oxygen-neon-magnesium cores. These variations affect crystallization temperatures, lattice structures, and cooling rates. For example, an oxygen-neon-magnesium black dwarf crystallizes at slightly higher temperatures, slowing heat loss for several trillion years. Low metallicity carbon-oxygen black dwarfs cool more efficiently, reaching near absolute zero sooner. This results in a population of black dwarfs with varying thermal and structural properties. Encounters between black dwarfs and brown dwarfs, neutron stars, or surviving red dwarfs produce small perturbations that affect galactic dynamics over long timescales. Scattering events and ejections gradually reduce the number of bound remnants in galaxies. Over extremely long timescales, black dwarfs become the dominant baryonic component in many regions. The energy emitted by black dwarfs over trillions of years is negligible. Black dwarfs radiate almost entirely in extremely low-energy microwaves or radio waves, undetectable by current astronomical instruments. Other sources of radiation in the far future include black holes, rare neutron stars, and the occasional surviving red dwarf. The transformation of white dwarfs into black dwarfs occurs over hundreds of trillions of years. During this time, white dwarfs cool and crystallize, while the cosmos continues expanding. Black dwarfs represent the late-stage remnants of stars in the universe, galactic drift, and cosmic isolation. With black dwarfs now populating galaxies, the universe begins to enter a profoundly lonely phase. The luminous interactions that once defined cosmic neighborhoods, starlight, supernovae, and energetic stellar winds are now gone. What remains is a universe of silent remnants drifting in isolation, as the expansion of space itself stretches the distances between galaxies to unimaginable scales. Even before the formation of black dwarfs, gravitationally bound systems like galaxies and clusters were not static. Two-body interactions, mergers, and the dynamics of dark matter halos constantly reshaped these systems. In the next trillion years, these processes continue, but the overarching influence comes from the accelerated expansion of the universe, driven by dark energy. Observations today place the dark energy density at roughly 6.9 1 times 10 to the power of negative 30 grams per cubic centimeter, a seemingly minuscule value, yet over vast distances and time, it dominates cosmic dynamics. Galaxies not gravitationally bound to one another begin receding faster, effectively disappearing from each other's observable universe. The Milky Way and Andromeda merger, expected within the next 4-5 billion years, will form a massive elliptical galaxy, sometimes called Milkdromeda. Other galaxies in the local group, such as triangulum or dwarf satellites, may be absorbed or ejected. Beyond the local group, recession velocities increase with distance due to cosmic expansion. By 100 billion years, galaxies in the Virgo supercluster will cross the cosmic event horizon, preventing their light from reaching other galaxies outside local gravitationally bound regions. In the far future, only local galaxies or galaxy clusters will remain visible within each other's observable horizon. Distant structures appear to vanish due to the expansion of space exceeding the speed of light. Simulations indicate that galaxies separated by more than roughly 16 billion light-years will be permanently isolated. This separates the universe into spatially disconnected regions. Within galaxies, gravitational interactions among remnants remain active but muted. Black dwarfs, neutron stars, and remaining red dwarfs occasionally exchange energy through close passes. Two-body relaxation processes, which cause objects to exchange momentum and sometimes escape the galaxy entirely, continue over timescales between 10 to the power of 17 and 10 to the power of 19 years. A significant fraction of remnants is gradually ejected into intergalactic space, becoming solitary wanderers. Even in clusters, these objects slowly migrate toward the outskirts, leaving the central regions dominated by supermassive black holes and the rare, tightly bound remnants. As the universe expands, intergalactic gas becomes increasingly rarefied. The average density of baryonic matter in intergalactic space is currently around 10 to the power of -7 particles per cubic centimeter. Over time, this density decreases further as gas is consumed or dispersed. Black dwarfs, neutron stars, and black holes remain as the primary massive objects, while new star formation ceases due to the lack of gas. Rogue objects, including black dwarfs, brown dwarfs, and neutron stars, ejected from their original galaxies, drift through near-perfect vacuum. These intergalactic wanderers move at speeds determined by their last gravitational interactions, typically tens to hundreds of kilometers per second. Over hundreds of trillions of years, many travel millions of light-years from any galactic structure. Interactions among these objects remain extremely rare. Galaxy mergers continue, but on an ever-declining scale. Distant galaxy groups, already moving apart due to dark energy, eventually reach relative velocities exceeding 1,000 kilometers per second, preventing new gravitational captures. Within the local group, however, simulations suggest that Milkdromeda will absorb or gravitationally scatter any remaining dwarf galaxies over the next 10 to the power of 11 years, leaving a solitary, massive elliptical galaxy as the final bastion of baryonic matter in its region. Its halo may contain hundreds of billions of black dwarfs and other stellar remnants. Yet beyond its periphery, the universe is almost entirely empty. As galaxies drift apart, the mean free path of photons, neutrinos, and other low-energy particles increases. Cosmic microwave background radiation continues cooling, eventually reaching temperatures below 10 to the power of -30 Kelvin over quadrillions of years. With the absence of luminous sources, energy gradients approach negligible levels. Cosmic structures persist, but the energy available for interactions is extremely low. The role of dark matter in this era is particularly notable. While dark matter does not radiate, it continues to influence the motion of remnants within galaxies. Galactic halos, composed predominantly of dark matter, provide the gravitational scaffolding for black dwarfs and neutron stars. Over trillion-year timescales, dynamical friction and tidal interactions cause some remnants to migrate toward halo centers, eventually contributing mass to the supermassive black holes at the cores of galaxies. Yet this process is slow, and for most isolated remnants, dark matter is the only persistent force shaping their trajectory. Even as galaxies become isolated, occasional high-energy events remain possible, though extremely rare. Collisions between black dwarfs, mergers of neutron stars, or encounters with residual gas pockets can produce brief flashes of radiation or gravitational waves. Simulations indicate frequencies on the order of one event per 10 to the power of 14, 10 to the power of 16 years per cubic parsec. For most of the universe, such energetic events are extremely infrequent. Intergalactic black dwarfs drift for tens or hundreds of millions of light-years, rarely encountering another star or remnant. Their motion is determined by initial ejection velocities and the gradual influence of dark energy. Over 10 to the power of 17 years, the average distance between such objects exceeds megaparsec scales. Spatial separation and expansion dominate the relative positions of these remnants. In a universe where galaxies, clusters, and black dwarfs are widely separated, the distribution of energy becomes nearly uniform. Gravitational potential energy is largely unavailable for large-scale processes, and radiative energy is extremely low. Usable energy remains primarily in rare subatomic decay or the eventual evaporation of black holes. As the universe grows colder and more diffuse, each gravitationally bound system, from galaxies to clusters, forms a distinct observable region. Light from outside these horizons cannot reach the system, creating causal boundaries. Observers in Milkdromeda would see only their galaxy and a few nearby companions, while other regions remain beyond observable reach. In this epoch, most baryonic matter exists as black dwarfs, neutron stars, or ejected remnants, while dark matter dominates large-scale structure. The intergalactic medium has an average density below 10 to the power of -10 particles per cubic centimeter. Thermal processes are minimal, and gravity governs the motion of objects. Even gravitational interactions become rare as distances increase compared to earlier cosmic epochs. The age of stellar remnant collisions. Even as galaxies drift into isolation and black dwarfs dominate their environments, the universe remains a stage for rare, extraordinary events. Over unimaginably long timescales, gravity continues to orchestrate encounters between stellar remnants, white dwarfs, neutron stars, black dwarfs, and rogue planets, resulting in collisions that, although infrequent, release energy on scales that dwarf anything in today's universe. This epoch, stretching from roughly 10 to the power of 14 to 10 to the power of 20 years, can be called the Age of Stellar Remnant Collisions, where cosmic drama is confined to sparsely scattered, high-energy interactions. The first major source of collisions arises from white dwarf and black dwarf encounters within isolated galaxies. As two-body relaxation continues over quadrillions of years, close gravitational interactions occasionally send these remnants on collision courses. While typical ejection speeds from galaxies range from 10 to 100 kilometers per second, some black dwarfs collide at relative velocities exceeding 1,000 kilometers per second, converting kinetic energy into heat and transient luminosity. The resulting collisions can briefly raise the temperature of carbon-oxygen cores to millions of Kelvin, producing bursts of radiation, predominantly in the X-ray spectrum. These events, although far dimmer than supernovae of earlier cosmic eras, represent the last substantial release of light from baryonic matter. Neutron stars contribute another dimension to these collisions. Although most neutron stars will have cooled to surface temperatures below 10 to the power of 5 Kelvin within the first trillion years, their extreme densities, around 10 to the power of 17 kilograms per cubic meter, allow for large energy releases if collisions occur. Simulations predict that neutron star mergers in isolated regions can produce gravitational wave bursts with energy on the order of 10 to the power of 47 joules. Neutron stars retain strong magnetic fields, often exceeding 10 to the power of 12 Gauss, which amplify energy emissions and generate brief jets of relativistic particles. The frequency of such events is very low, approximately 1 per 10 to the power of 15 years per cubic parsec. Rogue planets and smaller remnants also play a role, ejected from their parent systems during the two-body relaxation of galaxies. These objects travel vast distances in intergalactic space. Occasionally, gravitational interactions bring them into direct collisions with stellar remnants, especially in the dense cores of isolated galaxies or globular clusters. While the energy released is orders of magnitude less than a stellar collision, it is sufficient to briefly melt the surface of a black dwarf or vaporize a smaller planet. Over 10 to the power of 16 years, these low-energy collisions contribute marginally to the redistribution of mass within isolated systems, subtly altering trajectories of remnants and providing the only minor sources of localized radiation. In addition to ordinary stellar remnants, compact objects resulting from rare processes, such as magnetized white dwarfs or exotic neutron star variants, can participate in collisions. Observations of present-day systems, like the magnetar SGR 1000, 800, and 6-20, suggest that magnetic energy can rival gravitational energy in compact objects. Collisions involving magnetized remnants could briefly release electromagnetic energy exceeding 10 to the power of 46 joules, producing radiation in the X-ray and gamma-ray bands, though these events are extremely rare. Binary systems, if they survive ejections and galactic isolation, represent another avenue for collision. Tight binaries of white dwarfs or neutron stars gradually spiral inward due to gravitational wave emission, a process that continues long after luminous stars have vanished. For a typical white dwarf binary, with orbital periods on the order of hours, the merger can occur over 10 to the power of 14, 10 to the power of 15 years, producing a brief surge of thermal and kinetic energy. The merger products may collapse into neutron stars or low-mass black holes. Such collisions are rare, approximately one event per isolated galaxy per trillion years. Globular clusters, which survive the early era of galactic dispersal, act as sites for stellar remnant collisions. These dense stellar assemblies, often containing 10 to the power of 4, 10 to the power of 6 remnants within radii of a few parsecs, facilitate close encounters. Within such clusters, black dwarfs, neutron stars, and brown dwarfs occasionally collide or exchange momentum, producing phenomena like tidal disruption flares. Gravitational encounters can eject some remnants entirely, adding to the intergalactic population of rogue black dwarfs and planets. Over 10 to the power of 17 years, most clusters gradually lose density due to ejections, leaving only sparsely populated cores. The cumulative energy released from stellar remnant collisions is small compared to the luminous past of the universe. A collision between two 0.6 solar mass black dwarfs traveling at 500 kilometers per second releases roughly 1 times 10 to the power of 37 joules of kinetic energy, which is detectable only locally. Neutron star mergers produce energy comparable to the brightest supernovae of today, but occur extremely rarely, so most regions of the universe experience negligible interaction. Rogue black dwarfs and neutron stars interact with dark matter subhalos. Although the energy from dark matter interactions is small, gravitational perturbations can slightly alter remnant trajectories, occasionally causing collisions. Simulations suggest that over 10 to the power of 18 years, a measurable fraction of remnant mergers may result from such interactions. Dark matter, while invisible and non-radiative, continues to influence the distribution of baryonic remnants through its gravitational effect. Over longer timescales, low-probability catastrophic collisions can occur. In regions where remnants accumulate, such as the centers of merged galaxies or collapsed globular clusters, massive black dwarfs or dense neutron stars may collide, producing localized energy bursts. These rare events might form small black holes or trigger python-nuclear reactions in neutron star cores, temporarily releasing radiation and particles. Probabilities are extremely low, approximately one such event per 10 to the power of 20 years per cubic megaparsec. The age of stellar remnant collisions is marked by a gradual reduction in frequency. As remnants drift further apart due to galactic isolation and accelerated expansion, collisions become exceedingly rare. By 10 to the power of 20 years, even the most massive elliptical galaxies, containing hundreds of billions of remnants, experience only occasional merger events. Isolated black dwarfs and neutron stars in intergalactic space largely cease interacting, drifting for trillions of years without collisions. Thermal effects from these collisions, while brief, leave lasting imprints. A merged white dwarf may crystallize differently due to the redistribution of mass and energy, slightly altering the internal lattice structure. Neutron star collisions can produce heavy elements such as gold, platinum, and uranium, though the quantities are negligible compared to the universe's past nucleosynthesis. These chemical byproducts, scattered in small quantities, may eventually be captured by other remnants or expelled into intergalactic voids, forming the final elemental signatures of baryonic evolution. Gravitational waves from remnant collisions are the last observable signals from baryonic matter. Unlike electromagnetic radiation, gravitational waves propagate unimpeded across empty space, carrying information about mass, velocity, and energy. With collision frequencies declining and distances growing to megaparsec scales, these signals become extremely rare. The rise of supermassive black hole dominance. As the age of stellar remnant collisions fades into near silence, the universe enters a new chapter dominated not by stars or collisions, but by the most massive and enduring objects ever to exist: supermassive black holes. These giants, residing in the cores of galaxies, gradually assert control over their environments as luminous sources vanish, stellar remnants cool, and cosmic expansion isolates galactic islands. Over timescales stretching from 10 to the power of 20 years to 10 to the power of 100 years, supermassive black holes become the final sculptors of structure in the cosmos, governing the motion of any remaining matter and defining the last gravitational landscapes. The rise of supermassive black holes is rooted in the universe's earlier history. Today, central black holes range from Sagittarius A at 4.1 million solar masses to TON 618 at 66 billion solar masses. These formed through stellar collapse, accretion, and mergers. As galaxies merged during the stelliferous and degenerate eras, central black holes coalesced, producing increasingly massive singularities. After stellar collisions cease and remnants largely disperse, supermassive black holes dominate the gravitational dynamics within their host galaxies. In the near future, on cosmic timescales, remnant ejections and galactic mergers consolidate mass into central black holes. Simulations predict that over the next 10 to the power of 21 years, most residual stellar remnants and low-mass black dwarfs, in a typical massive galaxy spiral toward the galactic core due to dynamical friction, and are accreted. Sparsely populated globular clusters contribute material over extremely long periods, delivering mass through gravitationally guided migration. Accretion during this late stage is limited. Interstellar and intergalactic gas has been depleted, leaving black holes to consume only stellar remnants or rogue objects. The gravitational binding energy released remains significant. A single infall of a 0.6 solar mass black dwarf releases approximately 10 to the power of 37 joules, briefly heating the surrounding region and emitting X-rays or gamma rays. These events occur infrequently. The most massive, supermassive black holes, like TON 618, may grow through mergers with smaller black holes. Although cosmic expansion prevents most galactic encounters, residual satellite galaxies or captured remnants can contribute mass. A merger between two 10 to the power of 9 solar mass black holes releases more than 10 to the power of 54 joules in gravitational waves. These waves propagate through empty space, carrying information about the masses and spin rates of the black holes. Over time, such mergers can produce black holes approaching 10 to the power of 11 solar masses in isolated regions. An intriguing aspect of these black holes is their ability to eject remnants via gravitational slingshot effects. When multiple black holes interact within merged galactic cores, three-body encounters can accelerate smaller black holes or remnants to velocities exceeding 10,000 kilometers per second, allowing them to escape the galaxy. These ejected remnants enter intergalactic space as solitary objects, increasing the distribution of matter beyond galaxies. Spin dynamics add another layer of complexity. Observations indicate that many supermassive black holes retain high spin rates, often approaching 99% of the maximal Kerr limit acquired through accretion and past mergers. Spin affects the distribution of any residual matter through relativistic frame dragging, subtly shaping the orbits of nearby remnants. Over trillions of years, this spin may influence the ultimate distribution of mass near the black hole, but only on scales of tens to hundreds of parsecs. Farther out, dark matter halos continue to dominate motion, while distant black dwarfs and neutron stars drift in near-complete isolation. Even in these extreme conditions, radiation persists, though faint. Hawking predicted that black holes emit Hawking radiation, a process inversely proportional to mass. For supermassive black holes, this radiation is exceedingly weak, with temperatures below 10 to the power of -14 Kelvin for objects like Sagittarius A. Over timescales approaching 10 to the power of 100 years, even the largest black holes will gradually evaporate, releasing energy primarily in low-energy photons and neutrinos. Until that time, they interact only within falling remnants according to gravitational dynamics. The presence of supermassive black holes reshapes the internal structure of galaxies. In previously merged systems, simulations predict that gravitational interactions with the central black hole remove most stars and remnants within roughly 110 parsecs, creating a black hole desert. The outer halos retain sparse populations of black dwarfs, neutron stars, and ejected remnants. Over time, the density profile flattens, leaving galaxies with most mass concentrated in the central black hole. Gravitationally bound galaxy clusters are affected by the growth of central supermassive black holes. In the local group and other dense clusters, central black holes dominate the mass budget. Individual galaxies lose distinct structure as stars, remnants, and dwarf galaxies are accreted or ejected. The resulting bound system may be dominated by one or a few central black holes separated by tens to hundreds of kiloparsecs. Cosmic expansion causes clusters outside these bound systems to move beyond the cosmic horizon. The growth of supermassive black holes coincides with a decline in baryonic interactions. Collisions between black dwarfs, neutron stars, or rogue planets become exceedingly rare. Most objects are either accreted by central black holes or ejected into intergalactic space. Energy release from Hawking radiation or gravitational waves continues at low levels and is minor compared to earlier energetic events. Interestingly, black hole binaries and hierarchical multiples continue to influence dynamics. When two supermassive black holes merge, the resulting recoil caused by asymmetric gravitational wave emission can propel the new black hole at speeds up to 5,000 km per second, potentially ejecting it from the host galaxy. Such events redistribute mass across intergalactic space and create isolated supermassive black holes that continue to exert gravitational influence on surrounding dark matter halos. Over the span of 10 to the power of 23 to 10 to the power of 100 years, the universe evolves from a structured cosmos of stars, remnants, and galaxies to a state where supermassive black holes dominate, either in isolation or within merged galactic cores. Hawking radiation causes these black holes to slowly dissipate over time. They continue to influence motion, gravitational dynamics, and accrete any nearby baryonic material. Central black holes, such as Sagittarius A and TON 618, continue to influence merged galaxies and cluster mass budgets. Rogue remnants are ejected, galaxies drift apart, and collisions among smaller objects are extremely rare. Over long time scales, black holes accrete material and merge, while stars and galaxies are no longer significant contributors to dynamics. Eventually, processes such as proton decay and matter dissolution affect baryonic matter, leaving black holes, radiation, and dark matter as the primary components of the universe. Proton decay and the fate of matter. As supermassive black holes assert their dominance, the universe enters a deeper, subtler transformation. Gravity still governs motion, collisions become vanishingly rare, and remnants drift through vast emptiness. But even the most enduring structures, the atoms themselves, face a slow, inevitable decay. The concept of proton decay emerges as one of the most profound aspects of cosmic evolution, dictating the ultimate longevity of baryonic matter, the very substance of stars, planets, and living beings. Over timescales of 10 to the power of 34 to 10 to the power of 36 years, protons may spontaneously disintegrate, reducing the universe to radiation and leaving only black holes and exotic relics to define its structure. Current experimental physics provides indirect information about proton stability. The Super Kamiokande experiment in Japan has monitored over 50,000 tons of ultra-pure water for decades, searching for signs of proton decay, such as emission of positrons and neutral pions. No confirmed events have occurred, establishing a lower bound for proton half-lives at approximately 6 times 10 to the power of 34 years. Next-generation experiments like Hyper-Kamiokande aim to increase detection sensitivity by nearly an order of magnitude, which could test decay models predicted by grand unified theories. The process of proton decay, if it occurs, is extremely slow. In a single hydrogen atom, the proton may survive for 10 to the power of 34 years or more, but the cumulative effect across vast numbers of atoms leads to the disappearance of ordinary matter. Planets, comets, and asteroid remnants will gradually lose atomic structure. Over 10 to the power of 36 years, chemical elements such as carbon, oxygen, iron, and silicon will break down, leaving photons, neutrinos, and black holes as the primary remaining structures. White dwarfs and black dwarfs will also lose their atomic components over time. Neutrons, while stable within atomic nuclei, decay outside nuclei, with a lifetime of roughly 885 seconds. Over cosmic timescales, proton decay dominates. In composite objects such as black dwarfs, neutron stars, or planetary remnants, proton decay gradually reduces structural integrity. A white dwarf composed primarily of carbon and oxygen will, over 10 to the power of 35 years, lose nucleons to decay, reducing mass and converting matter into energy according to the equivalence principle. This process contributes to a diffuse background of photons and light leptons. This era also affects complex molecules and residual solid matter. As protons decay, chemical bonds break, and molecules such as water, methane, or complex carbon chains cannot persist. Minerals like quartz, olivine, and iron oxides also break down into fundamental particles. Over 10 to the power of 36 years, the universe contains only radiation, neutrinos, and remaining black holes. The distribution of decayed matter is generally uniform across the cosmos, with local variations near massive black holes. Hawking radiation from these black holes can interact with decaying baryonic matter, slightly increasing photon density nearby. These interactions create minor anisotropies in radiation and energy distribution around massive objects, providing a measurable local effect on particle distribution. Proton decay also affects galactic remnants and intergalactic clouds. In the voids between galaxies, sparse hydrogen, helium, and residual heavier elements gradually break down. Interstellar hydrogen clouds, previously potential sites for star formation, are consumed at the atomic level. Over 10 to the power of 36 years, these clouds fully dissolve, leaving only diffuse radiation and black holes. Interestingly, proton decay also affects the evolution of black dwarfs. These long-lived remnants, which survive tens of trillions of years after the stelliferous era, gradually lose mass as their constituent protons decay. Carbon-oxygen cores slowly shrink and emit energy over time. The timescale for full disintegration corresponds to the estimated upper limits of proton half-lives. Eventually, black dwarfs convert their mass into radiation and leptons. Neutron stars also experience proton decay over 10 to the power of 35, 10 to the power of 36 years. As protons decay, degeneracy pressure decreases, and neutron stars lose mass, emitting energetic leptons and photons. After proton decay is complete, only black holes remain as long-lived matter structures, while the rest of the baryonic matter has converted to radiation and leptons. The physics of proton decay has implications for particle physics and cosmology. Models based on SU5 and SO10 grand unified theories predict multiple decay channels, such as positrons with neutral pions or kaons with neutrinos. Each decay releases approximately 10 to the power of negative 10 joules per nucleon. Over extreme timescales, the cumulative effect leads to the disappearance of atomic structures. Residual cosmic rays and high-energy neutrinos from decaying baryons contribute to the background of energetic particles. Initially, the cosmic microwave background has densities exceeding 400 photons per cubic centimeter. Decayed remnants add low energy leptons and gamma photons, becoming increasingly diffuse. The energy spectrum decreases over time, approaching 10 to the power of negative 30 eV over extreme timescales, resulting in a universe where matter exists primarily as dispersed radiation and leptons. Proton decay affects hypothetical planets or artificial structures surviving from earlier cosmic epochs. Large bodies of iron, silicon, or carbon gradually lose atomic integrity and convert into radiation. Hypothetical megastructures, such as Dyson spheres around late black dwarfs, disintegrate atom by atom due to proton decay. The stability of any material structure becomes constrained by baryon decay over extreme timescales. As baryonic matter disappears, the universe's entropy increases. The conversion of nucleons into radiation and leptons contributes to a more uniform energy distribution. Estimates indicate that the total entropy approaches 10 to the power of 123 kb, corresponding to the maximum for a universe still containing black holes. Proton decay leads to a state dominated by radiation, neutrinos, and long-lived exotic particles. The interaction between decaying matter and supermassive black holes has limited effects. Black holes may absorb some decayed particles, but the low matter density in intergalactic space minimizes this contribution. Black holes remain as the long-lived gravitational structures, while proton decay gradually removes atomic matter. The universe increasingly consists of radiation, neutrinos, and gravitationally bound black holes. The universe as a black hole landscape, following the gradual decay of protons and the dissolution of baryonic matter, the universe undergoes a radical transformation. Stars, planets, and atomic structures are no longer part of the cosmic canvas. What remains are black holes of various masses, drifting in a universe increasingly devoid of ordinary matter. This stage, often referred to as the black hole era, spans timescales from roughly 10 to the power of 36 years to 10 to the power of 100 years, and it is defined by the predominance of gravity over all remaining structures. Black holes, both stellar mass remnants and supermassive behemoths, become the only entities capable of maintaining coherence, shaping a cosmos that is otherwise an empty, cold void. At the start of this era, stellar mass black holes dominated the landscape in terms of quantity. These objects, formed from the collapse of massive stars, range from about 5 to 50 solar masses. Observations of black hole candidates in the Milky Way, such as Cygnus X1 at roughly 21 solar masses, and GW190521, a merging system producing a remnant of 142 solar masses, reveal that black holes are both numerous and diverse. Over the first 10 to the power of 40 years of the black hole era, these stellar remnants remain largely isolated, drifting through interstellar and intergalactic space. Collisions between them are extremely rare, but when they occur, the energy released in gravitational waves can briefly outshine entire galaxies from the perspective of a distant observer. The next dominant class is intermediate mass black holes, ranging from 10 cubed to 10 to the power of 5 solar masses. These objects often reside in dwarf galaxies or cluster cores and are thought to form from repeated mergers of smaller black holes during earlier cosmic epochs. For example, simulations of globular cluster evolution suggests that repeated interactions among stellar mass black holes can produce a 10-cubed, 10 to the power of 4 solar mass intermediate black hole over a few trillion years. Intermediate black holes can gravitationally attract surrounding remnants and may merge with supermassive black holes over long timescales. At the top of the hierarchy stand supermassive black holes, which are now virtually uncontested. Objects like Sagittarius A star, with 4.1 million solar masses, or TON 618, at 66 billion solar masses, remain the most massive coherent structures. Their gravitational influence extends across tens to hundreds of kiloparsecs, dominating the motion of any nearby remnants or intermediate black holes. Occasionally, two supermassive black holes may interact following galactic mergers, producing gravitational wave emissions detectable in principle over vast distances. These events are exceedingly rare, but define the extreme end of the black hole landscape, forming the universe's most massive structures before eventual evaporation. A remarkable feature of the black hole era is the distribution of mass across cosmic voids. With baryonic matter largely eliminated, the universe consists mainly of gravitational attractors. Typical interstellar distances of a few parsecs grow into megaparsecant scale separations between black holes due to cosmic expansion. By 10 to the power of 40 years, simulations suggest that the average separation between stellar mass black holes may exceed 1 parsec in galaxy remnants, while supermassive black holes remain gravitationally bound to small clusters of residual dark matter. Black hole interactions occur but remain rare. Gravitational interactions, although rare, can influence black hole populations over long timescales. Close encounters between black holes can produce gravitational slingshot effects, ejecting lower mass black holes into intergalactic space at speeds up to several thousand kilometers per second. This process disperses stellar mass and intermediate black holes, leaving the most massive, supermassive black holes in relatively stable positions within remnant galactic cores. The energy output of black holes during this era is minimal but non-zero. Hawking radiation becomes increasingly relevant as smaller black holes evaporate over roughly 10 to the power of 64 years for a 1-0 solar mass black hole. This radiation is extremely faint, with temperatures in the nanokelvin range, and constitutes one of the final sources of electromagnetic energy aside from particle interactions. Larger black holes, including supermassive ones, emit negligible Hawking radiation due to their mass. Quantum processes continue at very low energy scales throughout the universe. The black hole era also demonstrates the role of mass hierarchy. Stellar mass black holes evaporate first, followed by intermediate mass black holes, while supermassive black holes persist up to 10 to the power of 100 years. The remaining population of black holes becomes dominated by the largest objects. Surviving dark matter or long-lived exotic particles continue to interact gravitationally with these black holes. Interestingly, binary and multiple black hole systems remain significant. Pairs of stellar mass or intermediate mass black holes can orbit one another for trillions of years, slowly emitting gravitational waves and tightening their orbits. In rare cases, a merger may produce a recoil effect, propelling the resulting black hole at velocities sufficient to escape its local gravitational well. Such rogue black holes drift through the intergalactic void indefinitely, occasionally encountering other black holes over timescales of 10 to the power of 50 years or more, creating rare but consequential interactions. Another facet of this era is the interaction with dark matter halos. While ordinary matter has largely decayed, dark matter persists and continues to influence black hole motion. Supermassive black holes within these halos can slowly accrete dark matter, though the process is limited by extremely low particle density, often below 10 to the power of -24 grams per cubic centimeter. Over extremely long timescales, even minor accretion can slightly modify the black hole's mass and spin. Cosmological expansion shapes the black hole landscape. Distant black holes recede from one another at velocities exceeding the speed of light relative to co-moving observers due to space expansion, isolating clusters and preventing interactions. Within a few 100 billion years, most supermassive black holes outside gravitationally bound systems drift beyond the cosmic horizon, leaving isolated black holes as the primary visible structures in their local regions. Gravitational wave signals provide the only detectable activity from these remnants for external observers. Mergers between stellar mass and intermediate black holes emit waves with amplitudes on the order of 10 to the power of -21 megaparsec distances, while supermassive mergers produce waves capable of influencing spacetime across hundreds of megaparsecs. These events are exceedingly rare. By the time the universe reaches 10 to the power of 50 years, most black holes have either evaporated, merged, or drifted so far apart that gravitational interactions are effectively negligible. Only the largest supermassive black holes remain isolated. The black hole era also introduces the concept of a post-baryonic horizon, the practical limit beyond which no significant structures remain. With proton decay and stellar evaporation complete, and Hawking radiation providing negligible energy, black holes dominate both energy density and gravitational influence. Black holes are the primary gravitational sources within otherwise sparse regions of the universe. Eventually, even supermassive black holes begin to lose mass through Hawking radiation, though the timescales are extremely long. A black hole of 10 to the power of 9 solar masses will take roughly 10 to the power of 87 years to evaporate, while the largest known black holes, such as TON 618, could persist for nearly 10 to the power of 100 years. As evaporation continues, low-energy photons and neutrinos are emitted, contributing to a diffuse radiation background, Hawking radiation, and the final light sources. As the universe settles into its black hole-dominated phase, darkness rules nearly everywhere. Ordinary stars are gone, galaxies have largely dissolved, and baryonic matter has decayed or drifted away. Yet, even in this deep cosmic night, black holes themselves become a faint source of light, producing a phenomenon predicted by Stephen Hawking in 1974, Hawking radiation. This subtle emission is the last form of electromagnetic and particle radiation to persist in the cosmos, marking the transition from a universe of massive remnants to one increasingly defined by diffuse energy. Hawking radiation arises from quantum effects near the event horizon of a black hole. Virtual particle-antiparticle pairs spontaneously form throughout space, but near a black hole, the intense gravitational field can separate these pairs. Occasionally, one particle falls into the black hole while the other escapes, appearing as radiation. The smaller the black hole, the higher its temperature and the more energetic the emitted particles. Stellar mass black holes, once billions of years old, remain cold by human standards, radiating at temperatures around 10 to the power of -8 Kelvin, far below the cosmic microwave background of today. Supermassive black holes, with millions or billions of solar masses, are even colder, radiating near 10 to the power of -14 Kelvin. During the first stages of this radiation-dominated transition, the universe still contains a mix of black holes. A 10 solar mass black hole, for example, will continue evaporating via Hawking radiation for roughly 10 to the power of 64 years. By this time, the surrounding space is extremely sparse, and even the faint radiation is one of the only detectable energy sources. The emitted photons and particles are extremely rare and low in energy, but they persist as measurable emissions from black holes. Hawking radiation is not limited to photons. The process also emits neutrinos, electrons, positrons, and in the final stages, heavier particles. For small black holes nearing complete evaporation, the temperature rises sharply, potentially reaching 10 to the power of 12 Kelvin, briefly releasing a burst of gamma rays, neutrinos, and exotic particles. However, such events are extraordinarily rare, given the expected distribution of black hole masses. Most supermassive black holes in the universe, including Sagittarius A star or TON 618, remain so massive that their Hawking radiation stays vanishingly faint for tens of orders of magnitude longer than the age of the universe today. The spatial distribution of Hawking radiation follows the distribution of surviving black holes. In the local remnants of galaxies like Milkomeda, intermediate mass black holes emit more energetic radiation than isolated stellar mass black holes drifting in the void. These emissions are extremely dilute, with photon fluxes often less than 1 particle per cubic meter. The radiation spectrum is thermal, but peaks at frequencies far lower than visible light, often in the microwave or radio regime for massive black holes, with temperature scaling inversely with mass. By the time stellar mass black holes have largely evaporated, around 10 to the power of 64 years, intermediate mass black holes remain as the next significant sources of Hawking radiation. These objects, between 10 cubed and 10 to the power of 5 solar masses, continue emitting for roughly 10 to the power of 70 to 10 to the power of 76 years. The faint emissions contribute to low-energy interactions with long-lived particles and dark matter remnants. Supermassive black holes represent the longest-lived sources of Hawking radiation. For black holes like TON 618, evaporation timescales extend to nearly 10 to the power of 100 years. Their radiation remains essentially undetectable against the near-absolute zero backdrop of space, with particle energies far below 1 nanokelvin. Hawking radiation constitutes the only measurable energy emission from these objects. Interestingly, Hawking radiation results in a redistribution of mass energy as black holes lose mass and convert gravitational potential energy into radiation. This process slightly warms the surrounding void, though the effect is minuscule. For example, a 10 to the power of 5 solar mass black hole loses mass at roughly 10 to the power of negative 22 grams per second, producing an equivalent energy flux of 10 to the power of negative 5 ergs per second. The combined emissions from trillions of black holes over cosmic timescales create a faint, uniform radiation field long after stars have disappeared. Hawking radiation also causes interactions between black holes and remaining particles. As high-energy virtual particles escape the event horizon, they slowly inject energy into the environment. These particles can interact with long-lived neutrinos, hypothetical dark matter candidates, or any surviving baryons. Though the density of these particles is extraordinarily low, less than 10 to the power of negative 30 particles per cubic centimeter, fundamental forces govern these interactions. As stellar mass and intermediate mass black holes evaporate, only the largest supermassive black holes remain. The universe becomes a faintly glowing void with a radiation field composed mostly of low-energy photons and neutrinos. Black hole evaporation distributes energy across vast volumes, gradually reducing spatial variations in temperature and density. The spectral characteristics of Hawking radiation evolve as black holes shrink. Initially, radiation is predominantly low-frequency microwaves or radio waves. For small black holes nearing complete evaporation, the peak shifts to X-rays and gamma rays, producing transient bursts detectable across vast distances. For instance, a 10 to the power of 12 kilogram black hole in its final second emits roughly 10 to the power of 31 ergs, comparable to a small supernova, though these events are extremely rare. Over trillions of years, the universe experiences isolated bursts of radiation from evaporating remnants. Hawking radiation also affects residual cosmic structures. Rogue black holes passing through low-density regions can leave faint trails of energetic particles, slightly heating surrounding dark matter halos, or interacting with long-lived lepton. Over timescales of 10 to the power of 70 to 10 to the power of 100 years, these processes gradually redistribute energy across space. Even after the last intermediate mass black holes evaporate, the universe retains a diffuse sea of radiation and neutrinos. Photon densities fall drastically, but cosmic backgrounds persist. Current estimates suggest that after 10 to the power of 100 years, the energy density of this diffuse field will be less than 10 to the power of -20 erg per cubic centimeter, with temperatures near 10 to the power of -30 Kelvin. Many of these photons originate from Hawking radiation. The persistence of Hawking radiation also raises questions about detectability. Instruments or observers would be limited to detecting these faint emissions. For supermassive black holes, temperatures fall below 1/1000th of a nanokelvin, making direct observation effectively impossible. Hawking radiation continues to exist as a physical emission from these black holes. By the end of this radiation-dominated era, all black holes will have vanished, leaving only low-energy photons, neutrinos, and hypothetical long-lived exotic particles. Hawking radiation gradually converts the remaining mass of black holes into energy. The evaporation process occurs over extremely long timescales, up to 10 to the power of 100 years for the largest black holes, the photon and neutrino seas. After black holes have evaporated, the universe is left in a state that is at once almost unimaginably empty and subtly alive with remnants of its former energy. The dominant forms of this energy are not stars, galaxies, or even planets, but particles that have persisted since the earliest moments of cosmic history, low-energy photons and relic neutrinos. These particles form vast, diffuse seas that permeate every corner of the universe, carrying the last traces of its dynamic past. Photons, the carriers of electromagnetic radiation, now exist almost entirely as relics from previous epochs. The cosmic microwave background, once a faint glow at 2.7255 Kelvin shortly after the Big Bang, has cooled over trillions of years. After black hole evaporation, the photon sea reaches temperatures around 10 to the power of -30 Kelvin, an energy so low that the particles behave almost entirely like quantum fields rather than classical radiation. There are roughly 400 photons per cubic centimeter in today's universe, but over the next 10 to the power of 100 years, the expansion of space will dilute this number dramatically, leaving only a handful of photons per cubic kilometer of space. Alongside photons, neutrinos form an even more elusive component of this cosmic sea. Relic neutrinos, produced in vast numbers during the first second after the Big Bang, have an estimated density of 340 neutrinos per cubic centimeter today. Unlike photons, neutrinos interact extremely weakly with matter. Even in a universe filled with black holes and stars, most neutrinos would have passed through every planet, star, and black hole without ever interacting. After the evaporation of all black holes, these neutrinos remain as one of the last surviving particle populations, traveling at nearly the speed of light, but with energies reduced to 10 to the power of -31 to 10 to the power of -30 electron volts, effectively making them invisible and undetectable by any conventional method. The photon and neutrino seas are not uniform. Local variations in density remain from earlier cosmic structures, though these differences are minuscule. For example, regions that once contained superclusters now have slightly higher concentrations of relic photons due to the decay of black holes and the last emission of Hawking radiation. Even these variations are on scales of billions of kilometers, and cosmic expansion gradually reduces the contrast in density over time. Photon energies follow a near-perfect thermal distribution, with the peak wavelength shifting toward longer scales as the universe expands. Neutrinos, although nearly massless, contribute to the overall energy density and exert a tiny pressure on the surrounding spacetime, influencing the evolution of cosmic expansion in subtle ways. Together, these particles form a background energy that persists after all conventional matter has vanished. The photon sea also carries remnants from the universe's most energetic events. Gamma-ray bursts, supernovae, and quasar emissions have left faint imprints in the low-energy spectrum, stretched over large distances by cosmic expansion. The initial energy of these photons may have been billions of electron volts, but after 10 to the power of 100 years, they are reduced to levels far below a nanokelvin. Neutrinos carry information from processes that photons cannot reveal. Neutrino interactions in the early universe, particularly during the quark-gluon plasma phase and subsequent nucleosynthesis, created tiny anisotropies in the neutrino distribution. Though current detection methods cannot observe such low-energy relics, the anisotropies persist as subtle variations in density. Over vast timescales, these patterns are diluted by the expansion of space. Another critical aspect of this era is the interaction between residual particles and hypothetical, long-lived exotic species. Certain grand unified theories predict the existence of magnetic monopoles, sterile neutrinos, or supersymmetric particles with lifespans far exceeding the age of the universe. These particles, if they exist, may interact occasionally with photons or standard neutrinos, producing rare bursts of energy or minute shifts in local densities. The expected frequency of these events is extremely low, perhaps one interaction per cubic parsec every trillion years. The density of these particle seas also has measurable effects on cosmic expansion. Photons and neutrinos contribute to the overall energy-momentum tensor in general relativity, albeit weakly. As their energy dilutes, the expansion remains dominated by dark energy, which has a density of roughly 6.9, 1 times 10 to the power of negative 30 grams per cubic centimeter. As the universe expands, photons and neutrinos become increasingly sparse across vast regions of space. Despite the extreme sparsity of particles, the photon and neutrino seas still represent the primary carriers of information and energy. Any hypothetical observer in this epoch would find that these particles constitute nearly all measurable phenomena. Electromagnetic radiation from Hawking radiation has already faded. Black holes have evaporated, and matter has largely decayed. Only the diffuse sea of photons and neutrinos remains, persisting from early cosmic epochs. The evolution of these particle seas involves the gradual dilution of energy. As black holes vanish, energy is distributed among photons and neutrinos. Each remaining particle contributes to the total energy density, and over 10 to the power of 100 years and beyond, the particle number density decreases as the universe continues expanding. Interestingly, the photon and neutrino seas may interact with vacuum fluctuations. Even in regions devoid of conventional matter, quantum mechanics predicts occasional spontaneous particle-antiparticle pairs. While most of these virtual events annihilate immediately, rare fluctuations could interact with relic photons or neutrinos, creating tiny bursts of energy that propagate across the void. After the last black holes evaporate and matter has decayed or drifted beyond causal contact, photons and neutrinos define the remaining energy distribution. Their temperatures, densities, and spectral properties determine the conditions under which rare particle interactions or quantum processes could occur. By this stage, the universe is a vast, quiet expanse. Photons drift at the speed of light, neutrinos travel nearly as fast, and the density of particles has decreased to the point where interactions are extraordinarily rare. Subtle particle interactions, remnants of Hawking radiation, and the ongoing expansion of spacetime influence the remaining energy distribution. The photon and neutrino seas persist as the dominant particle populations. Transition to the dark era. The universe has entered a stage that can only be described as almost entirely empty, yet even this near-nothingness holds subtle traces of its explosive and luminous past. After the last black holes have evaporated and the seas of photons and neutrinos drift across the expanding void, the cosmos faces its next evolutionary stage, the transition into the dark era. In this epoch, which begins roughly 10 to the power of 100 years from now, all forms of conventional energy, light, and matter-driven activity diminish to levels that challenge comprehension. This transition unfolds over timescales of roughly 10 to the power of 105 to 10 to the power of 120 years. Physical processes during this period are measurable and predictable. Even in near-total emptiness, quantum fields, particle interactions, and the residual effects of cosmic expansion create a low-energy density environment. By this point, ordinary baryonic matter, protons, neutrons, electrons, has either decayed through predicted mechanisms or been dispersed beyond causal contact. If protons decay, as predicted by some grand unified theories, with a half-life of 10 to the power of 34, 10 to the power of 36 years, then virtually all atomic nuclei have disintegrated into lighter particles such as positrons, neutrinos, and gamma photons. Any remaining heavy isotopes have long since broken down, leaving a sparse distribution of fundamental particles drifting through space. Even if protons remain stable, the gravitational scattering that ejected remnants from galaxies over 10 to the power of 19 years ensures that most matter is spread thinly enough that interactions are negligible. Energy, once concentrated in stars, galaxies, and black holes, is now almost entirely diffused. The remnants of Hawking radiation from evaporated black holes still exist as low-energy photons and neutrinos, but their density is so small that collisions between particles are vanishingly rare. The photon temperature, already around 10 to the power of negative 30 Kelvin, continues to drop, approaching 10 to the power of negative 32 Kelvin over successive eons. Neutrinos, traveling nearly at light speed, contribute little to thermodynamic processes due to their weak interactions. The universe is effectively an ultra-dilute plasma of free particles, with space-time itself stretching relentlessly, carrying energy farther apart. Even in this extreme emptiness, gravity continues to shape what little remains. Over the course of 10 to the power of 100 and 10 to the power of 120 years, tiny clumps of matter may occasionally form through residual gravitational attraction. Minute clusters of protons, electrons, or neutrinos could coalesce to form structures far smaller and weaker than any star or planet. These structures are ephemeral and isolated, collapsing under gravity only to disperse through quantum tunneling, radiation pressure, or nearby particle interactions. Simulations suggest that these processes are extraordinarily rare, with one such event occurring perhaps once per 10 to the power of 15 cubic light-years per trillion years. Dark energy continues to dominate the expansion. The scale factor of the universe accelerates exponentially, and even the densest residual particle clusters are slowly stretched apart. Galaxies, which once formed intricate networks of clusters and filaments, have long ceased to exist as coherent systems. Any previously bound groups of particles are ripped apart by the accelerating expansion, leaving isolated particles that are causally disconnected from one another. Beyond a certain horizon, even light and neutrinos cannot traverse the expanding spacetime to interact. This expansion effectively creates countless causal islands, each containing only a few surviving particles or quantum fields. Temperature gradients, the engine of all energy transfer, are essentially gone. Without stars, black holes, or dense matter, there are no sources of localized heat. Any remaining energy is distributed across vast volumes, leaving gradients so weak that chemical reactions, nuclear processes, or conventional thermodynamic work are impossible. Localized variations exist only as tiny quantum fluctuations or rare high-energy particle events. These quantum fluctuations, arising from the uncertainty principle, become increasingly significant. In the absence of more energetic processes, vacuum fluctuations which produce virtual particle-antiparticle pairs represent the main source of dynamic activity. These virtual pairs typically annihilate almost immediately, but over trillions of eons, some fluctuations may interact with photons, neutrinos, or residual matter, creating extremely weak, sporadic bursts of energy. Exotic particles, if they exist, may also play a role in this transition. Theories predict the presence of long-lived particles, such as magnetic monopoles, sterile neutrinos, or WIMPs, also known as weakly interacting massive particles, with lifespans far exceeding the universe's current age. These particles could interact with relic photons or other exotic particles, producing tiny bursts of energy or rare collisions. The cosmic photon and neutrino seas, which dominated the preceding epoch, continue to exist. The photons drift apart due to cosmic expansion, their wavelengths stretching further into the infrared and radio regimes, while neutrinos carry energy and momentum across sparse regions of space. Their presence constitutes a diffuse energy field throughout the universe. Interestingly, gravitational waves from the distant past may also persist into this era. Collisions of black holes, neutron stars, and the last supermassive mergers generate waves that ripple through spacetime. Though their amplitude diminishes over time due to expansion, these gravitational disturbances carry energy across otherwise empty regions. In some rare regions, overlapping waves could produce infinitesimal gravitational interactions. Another characteristic of this era is space-time itself. As the universe expands, horizons form that separate regions of causally disconnected space. Particles that once might have interacted are now isolated, beyond each other's influence. The scale factor grows exponentially due to dark energy, and distances between particles increase faster than the speed of light. This era also marks the final phase for any remaining baryonic remnants. Even the last atomic nuclei, if they have not yet decayed, are left in environments with near-zero temperatures and near-zero interaction probabilities. Any residual chemical reactions are impossible, and nuclear fusion has long ceased. Planetary or stellar structures no longer exist. The dark era allows for the persistence of rare physical processes. Decay of ultra-heavy hypothetical particles or annihilation of virtual particle pairs may occur, providing low-level interactions over extremely long timescales. Over the next 10 to the power of 120 to 10 to the power of 125 years, the universe continues to approach a state where even these minimal processes fail. Photons and neutrinos are stretched across vast volumes so that their density approaches zero. Any residual gravitational attractions are negligible, and vacuum fluctuations become increasingly rare. The universe becomes a near-perfect vacuum. Even as visible matter, stars and galaxies vanish, fundamental forces continue to operate. Electromagnetism and gravity still influence particle behavior. Quantum fluctuations persist, and relativity continues to determine the geometry of expanding space, quantum vacuum and residual particle activity. Even in a universe stretched almost beyond recognition, where the last black holes have evaporated and matter has become extraordinarily sparse, something remarkable persists. The quantum vacuum. Far from being empty, this vacuum is a seething field of potentiality, teeming with ephemeral phenomena that challenge our understanding of space, energy, and time. As the cosmos transitions fully into the dark era, these subtle quantum processes become the dominant activity in an otherwise inert universe, offering the only traces of energy and interaction across the void. The quantum vacuum is governed by the uncertainty principle, which dictates that even in the absence of conventional particles, energy fluctuations spontaneously occur. These fluctuations create virtual particle-antiparticle pairs that appear and vanish in incredibly short spans of time. Lifetimes for these pairs can range from 10 to the power of -21 to 10 to the power of -18 seconds, depending on their mass and energy. Although they are fleeting, these pairs have measurable effects, influencing the cosmological constant, vacuum energy density, and even the propagation of light across immense distances. In a universe devoid of stars, galaxies, or conventional matter, such vacuum phenomena dominate the residual physical processes. Residual particles that survive the prior eras, such as free electrons, protons, or exotic particles like sterile neutrinos and hypothetical WIMPs, interact occasionally with these quantum fluctuations. These interactions are exceedingly rare, but not impossible. For example, a lone electron drifting through space may interact with a virtual photon or a neutrino, creating infinitesimal energy changes or scattering events. Over timescales of 10 to the power of 125 years, these tiny interactions become statistically meaningful, representing the only processes that generate energy differentials in an otherwise uniform cosmos. The vacuum itself contains measurable energy. Cosmologists estimate the dark energy density to remain around 6.9, 1 times 10, to the power of -30 grams per cubic centimeter, effectively constant across large volumes. This energy influences the accelerated expansion and interacts with quantum fields, potentially producing rare particle pair creation events. Some theoretical models include possibilities of forming microscopic structures, although these remain speculative in current physics literature. Over tens of trillions of eons, even the most resilient particles undergo changes. Hypothetical long-lived particles, such as magnetic monopoles or extremely massive WIMPs, may decay, releasing tiny bursts of energy. These decay events contribute to a minimal but persistent background of high-energy phenomena in a universe otherwise dominated by near-zero energy. Estimates suggest that a single monopole decay might release around 10 to the power of -9 joules of energy, barely detectable on cosmic scales, but significant when they are the only remaining sources of energy. Virtual particle production also influences the propagation of light and other particles across the universe. Even photons of extremely low energy, on the order of 10 to the power of -32 Kelvin, experience subtle interactions with vacuum fluctuations. These interactions can slightly shift trajectories or polarization, producing a sparse but non-zero mechanism for energy redistribution. Minute quantum processes introduce fluctuations in particle density and energy. Another feature of this era is the behavior of neutrinos. Neutrinos produced during earlier cosmic epochs drift almost entirely unimpeded. With densities around 340 neutrinos per cubic centimeter at the beginning of the dark era, their energy decreases with expansion. Interactions between neutrinos and virtual particles, or residual matter, can generate very small energy transfers over long timescales. The transition to vacuum-dominated dynamics highlights areas where current physical models are incomplete. Processes such as spontaneous vacuum polarization, where virtual particle pairs momentarily interact with background fields, can produce transient forces or energy fluctuations. These effects are subtle but measurable within certain theoretical frameworks. Cosmologists have proposed models in which microscopic structures arise from vacuum fluctuations. For example, small quantum knots or bubbles may temporarily increase local energy density before dissipating. These structures would be extremely small, on the order of the Planck length, and represent localized quantum field behavior. The interplay between virtual particles and relic high-energy remnants provides mechanisms for energy redistribution. Electrons interacting with vacuum fluctuations may emit extremely low-energy photons through a process similar to the dynamical Casimir effect. The energy involved is very small, on the order of 10 to the power of negative 30 joules per event. As the dark era progresses, expansion separates regions of quantum activity. These regions operate under the same physical laws, but become too far apart to influence one another. Rare high-energy events remain confined locally because of the large cosmic distances. Over timescales beyond 10 to the power of 135 years, these processes function on strictly local scales. Some theoretical models propose that vacuum fluctuations may occasionally nucleate new forms of matter or energy configurations, such as micro-black holes, localized high-energy photon bursts, or temporary condensations of exotic particles. The probability of such events is extremely low according to current calculations. The vacuum's dynamics also influence the behavior of spacetime on extremely long timescales. As the universe cools and energy gradients diminish, dark energy continues to drive expansion. Quantum fluctuations may slightly modulate this expansion on local scales, producing small variations in curvature or gravitational potential. Residual interactions between virtual particles and hypothetical long-lived exotic matter may lead to decay processes over extremely long timescales. If particles with lifetimes exceeding 10 to the power of 150 years exist, their decay could generate extremely low-frequency gravitational waves or faint radiation bursts. Quantum fluctuations, rare particle decays, and residual interactions persist over extremely long timescales. These processes represent the remaining measurable phenomena during the late dark era, and continue to produce low-level physical activity. By the end of this epoch, vacuum activity and rare particle events dominate the observable processes. Coherent structures, chemical reactions, and thermal gradients no longer occur. Virtual particles, residual neutrinos, long-lived exotic particles, and the expanding geometry of spacetime continue to operate under established physical laws, with observable effects occurring at extremely low probabilities and energies. At extreme timescales, continued cosmic expansion further reduces the frequency and intensity of residual physical processes. Spacetime deformation at extreme longevity. Over the incomprehensibly long ages that follow the evaporation of the universe's final black holes, spacetime enters a period where its own structure becomes the dominant feature of cosmic evolution. There are no galaxies left to stretch apart, no stars or remnants to drift through the void, and no black holes to define regions of spacetime curvature. What remains is the expansion itself, a silent, continuous transformation driven by the persistent push of dark energy. This follows the expansion into timescales where conventional astrophysical objects no longer matter, and only the fabric of spacetime remains active. Understanding this era requires turning attention toward how the universe behaves when particle interactions fade into negligible rarity, and when geometry, rather than matter, dictates the long-term evolution of the cosmos. The baseline for this stage is the WCDM model, which assumes a constant dark energy density of about 6.91 times 10 to the power of negative 30 grams per cubic centimeter. This value sounds tiny, but its persistence and uniformity mean it governs the ultimate fate of the universe. Long after matter and radiation have lost their influence, dark energy remains. Over vast durations, this constant background pressure stretches distances between all points in the universe exponentially. Since no new structures form and the last regions of localized curvature vanish with evaporating black holes, spacetime becomes an arena almost completely free of gravitational anchors. The universe continues expanding, regardless of whether anything inhabits it. Although the universe already experiences accelerated expansion today, the observable effects are modest because gravitationally bound structures still exist. Galaxy clusters remain intact and within them galaxies hold together through gravity. On the scale of trillions to quadrillions of years in the future, all bound structures will vanish. The cosmic metric continues to evolve, affecting distances, event horizons, and the probability of particle interactions. One of the most striking long-term consequences of constant dark energy is the stability of the cosmic event horizon. Even as distances between objects continue growing, there remains a maximum boundary beyond which signals can never reach a given observer. Today, this boundary is roughly 16 billion light-years. In the distant future, as expansion accelerates, this horizon settles to a value around 17 to 18 billion light-years, depending on specific cosmological parameters. Beyond timescales of trillions of years, the horizon remains nearly constant, defining the maximum volume within which causal interactions can occur. During earlier cosmic epochs, horizons shaped what could be observed. In the far future universe, horizons determine what can exist in causal contact. With matter decayed or diluted to near-zero concentrations, the significance of the horizon becomes less about seeing distant objects and more about defining the volume within which any interaction remains possible. As expansion continues, the density of particles and photons drops to the point where the chance of two interacting within a horizon volume becomes practically zero. Over quintillions of years, even the rarest interactions approach impossibility because the expansion stretches the distance between particles faster than diffusion or random motion could bring them together. The deformation of spacetime becomes even more pronounced when considering the fate of wavelengths. The background radiation from earlier eras continues stretching, its wavelengths lengthening to scales comparable to astronomical distances. Photons that once vibrated at measurable energies now possess wavelengths spanning millions, then billions, then trillions of light-years. Eventually, individual photons occupy volumes so enormous that describing them as waves in space is more accurate than treating them as traveling particles. Neutrinos undergo a similar evolution, though their physical behavior remains influenced by their tiny but non-zero mass. After unimaginable time spans, they slow in the expanding geometry as the expansion cools them to energies approaching zero. The long-term changes in space-time also influence how quantum fields behave, with expansion continually increasing the physical scale across which fields exist. Fluctuations become less localized. The vacuum still produces virtual pairs of particles, but the background energy density continues falling as the universe grows. Over extreme durations, the average energy in any given region of spacetime becomes extraordinarily low. Quantum fluctuations persist because they are inherent to the nature of quantum fields. Yet the environment they occur in grows progressively emptier. This persistent expansion stretches the spatial regions associated with these fluctuations, influencing their lifetimes and scales, even though their underlying physics remains constant. An important aspect of spacetime deformation involves the growth of co-moving distances. In present-day cosmology, co-moving distance refers to spacing that grows with the expansion of the universe, representing the separation between points in the cosmic fabric. In the far-future universe, co-moving distances undergo enormous increases. Regions once separated by millions of light-years can grow to separations exceeding googles of light-years. Cosmologists describe these expansions in terms of scale factors, which increase by extremely large multiples during these epochs. The physical geometry of space also evolves toward uniformity. Irregularities in curvature, once caused by matter and gravitational fields, fade away as the universe expands and massive objects vanish. The geometry approaches a smoother, flatter form. Curvature from dark energy continues to exert a uniform outward push, without creating localized distortions, making expansion the dominant influence on large-scale geometry. This transformation also changes the practical basis for measuring time. In earlier eras, time could be referenced to astronomical processes, stellar life cycles, orbital periods, or cooling rates of cosmic backgrounds. In the far future, with these processes absent, cosmologists quantify time in terms of the expansion of the scale factor, relating changes in spacetime metric to the passage of time. Even after the universe reaches ages where expansion dominates earlier changes, it continues accumulating small but measurable effects. Distances grow, horizons maintain their size, and particle densities dilute. Expansion persists because dark energy remains constant. Over long durations, the energy of photons decreases, with typical energies dropping below detectable thresholds. Individual photons can have wavelengths comparable to the observable horizon, and their energy falls below levels required to initiate physical interactions. As spacetime continues stretching across long periods, interactions between particles become increasingly rare. Even if virtual particles appear momentarily, the large separations and low energy density reduce the frequency of real interactions to less than once per volume, vastly larger than the observable universe. Expansion effectively prevents interactions from occurring over these enormous scales. Under the WCDM model, spacetime deformation does not result in catastrophic events. It follows a continuous, predictable geometric evolution with no rip, tear, or collapse. Expansion continues indefinitely, with dark energy determining the rate of scale factor increase, while matter and radiation remain negligible. In this era, no new structures form, but expansion continues indefinitely. Distances increase without bound, and matter and radiation densities approach zero. Spacetime continues stretching under the influence of dark energy, with the large-scale metric evolving over time without abrupt changes. The heat-death landscape. By the time the universe drifts into the age of heat death, the last traces of structure have long since vanished. No stars, no planets, no black holes, not even the faintest flicker of gravitational binding remains anywhere. Yet the universe is not empty in the way a vacuum chamber on Earth appears empty. It is filled with relics so faint, so diffuse, and so evenly spread that they no longer drive change. The heat-death landscape is defined by uniformity, an evenly cooled ocean of particles and radiation, where nothing differentiates one region from another. This is the environment toward which all cosmic trends point, a state where energy remains, but none of it can be used to do work. Even though the universe contains energy in this distant era, that energy is not concentrated enough to fuel any process that would create order or motion. After the evaporation of the last black hole, the background temperature has fallen to a level only slightly above absolute zero. Values this small defy everyday description, but they are real, measurable quantities in theory. Temperatures so low that no natural mechanism can extract usable energy from them. Differences in temperature or density are needed for change, and by this stage, such differences have been erased. The cosmos becomes a thermodynamic desert, incapable of producing the gradients necessary for motion, chemistry, or structure. Every particle obeys the same stillness, drifting without direction in a sea that has no currents. Particles existing in this landscape occupy enormous volumes compared to earlier eras. A single photon can stretch across distances equal to billions of light-years, its wavelength too large to meaningfully interact with anything around it. Neutrinos, once abundant and energetic during the first seconds after the Big Bang, now drift with kinetic energies too small to register in any comparable reference. Their density remains measurable only in the sense that, on average, there are still a few hundred per cubic centimeter, but those cubic centimeters extend into a universe whose total volume expands without limit. The rarity of interaction becomes absolute. The probability that a relic neutrino will collide with another particle in this era is effectively zero, not simply because they are sparse, but because the expanding geometry continually separates them. Entropy, the measure of disorder, reaches values so high that conventional descriptions become less practical. On cosmic scales, entropy increased when stars burned fuel, galaxies formed, and black holes consumed matter. With these processes absent, the remaining entropy corresponds to energy uniformly distributed across space. Estimates for total cosmic entropy are extremely large, reflecting a near-uniform energy configuration with no significant gradients. During earlier epochs, cooling of the cosmic background radiation marked the passage of time. In the heat-death landscape, the temperature continues to fall asymptotically toward absolute zero. The decrease in energy per photon occurs extremely slowly and can only be measured over very long periods of cosmic expansion. Over such timescales, changes in photon energy are minuscule. Despite this stillness, the universe remains governed by quantum mechanics. Quantum fields permeate every region and continue their fluctuations even in a nearly energyless state. These fluctuations produce brief appearances of virtual particles, but the low background energy stretches the regions in which these events occur. While these quantum events are extremely short-lived and localized, they represent the only ongoing activity at microscopic scales. The particles that persist into this era are few and widely scattered. Relic photons are the most abundant leftovers from the earliest ages. Neutrinos remain the second most numerous, though far less energetic. Rare, long-lived particles, if any beyond neutrinos exist, survive in densities that appear nearly zero when compared to the vastness of space. Exotic particles theorized in earlier physics, such as hypothetical axions or remnants of supersymmetric processes, could exist in densities too low to influence anything. Their presence would have no effect on the large-scale state of the universe. The expansion swallows them into a geometry where their existence becomes statistically irrelevant. One feature of the heat-death environment is that co-moving distances expand dramatically. Distances between points increase to such a scale that comparisons between small and large separations become negligible. The expansion continues without bound, and the relative positions of particles or regions have limited practical meaning. Only the spatial metric continues to define separations between points. Yet, even in this low-activity universe, the laws governing spacetime remain in effect. Dark energy continues to contribute to the expansion, which propagates through regions containing very little matter or radiation. The expansion continues as dictated by the WCDM model, independent of the presence of structure. Heat death does not involve collapse or catastrophic events. The state corresponds to the exhaustion of usable energy and the absence of gradients. Curvature becomes nearly uniform, and large-scale structure ceases to evolve. Thermodynamically, the universe approaches a near-maximal entropy configuration. Free energy, which powered stars, galaxies, and planetary systems throughout cosmic history, becomes zero in the age of heat death. Energy exists, but cannot be extracted for work. Without gradients in temperature or density, each region of space is thermodynamically uniform, preventing processes that rely on energy differentials. The maximum entropy state prevents spontaneous structure formation. In earlier eras, turbulence, gravitational collapse, or quantum fluctuations could produce new arrangements of matter. After heat death, any temporary fluctuation of higher energy would be rapidly diluted by expansion, preventing the formation of stable structures. The heat death landscape continues indefinitely. Within the WLCDM model, there is no mechanism that reverses or halts expansion. The universe expands continuously, and energy gradients remain absent. Alternate end-state possibilities. The heat death scenario presents a picture of slow, inevitable stagnation. But modern cosmology suggests that the universe's fate may not be so singular. While the LCDM model points to eternal expansion into a maximally entropic state, several alternative end-state possibilities emerge when considering the complexities of dark energy, quantum fields, and the fundamental structure of spacetime. Each presents a radically different cosmic future, where the universe may not simply drift into inert uniformity, but undergo cataclysmic or transformative events. One of the most widely discussed alternatives is the Big Rip, a scenario tied directly to the properties of dark energy. Observations of Type Ia supernovae and cosmic microwave background anisotropies indicate that the universe's expansion is accelerating. If dark energy is not a cosmological constant, but instead a dynamic field with a density that increases over time, its repulsive effect could eventually overcome all other forces. In the Big Rip model, galaxies would first be torn apart, followed by star systems, planets, and finally atoms themselves. Current estimates suggest that if the dark energy density increases at a steady rate, this catastrophic end could occur around 10 to the power of 26 years from now. Galaxies like the Virgo cluster, currently spanning tens of millions of light-years, would disassemble long before the stars within them are disrupted. Systems similar to our solar system would be shredded as tidal forces overwhelm gravitational binding, leaving protons and electrons drifting individually across an ever-expanding void. Another proposed alternative arises from quantum field theory, vacuum decay. The Higgs field, responsible for giving particles their mass, could exist in a metastable state rather than a true vacuum. Current measurements, including the Higgs boson mass of 125.1 GeV and the top quark mass of 172.76 GeV, suggest that our vacuum may not be absolutely stable. In such a metastable universe, random quantum fluctuations could trigger a transition to a lower energy state, forming a bubble of true vacuum that expands at nearly the speed of light. Any region within this bubble would experience a reconfiguration of physical constants, altering fundamental interactions and structures at all scales. Some alternative scenarios involve a dynamic dark energy landscape, sometimes described as quintessence, where the equation of state changes over time. Instead of a fixed W, the energy density could vary in a way that temporarily halts or reverses expansion. In models where dark energy density decreases, the universe could experience a contraction phase, potentially leading to a big crunch. If the contraction is complete, space-time would collapse, compressing all matter and radiation into an extremely high-density state. Temperatures could reach trillions of Kelvin, recreating conditions similar to those at the very beginning of the universe. While observational evidence for such a scenario is limited, it is a mathematically consistent solution to Einstein's field equations. Cyclic or oscillatory models combine the concept of a big crunch with quantum effects. In these scenarios, the collapse of the universe is followed by a new expansion phase. Studies of loop quantum cosmology suggest that spacetime may have a discrete structure at the Planck scale, allowing for a bounce rather than a singularity. Some models indicate that entropy could partially reset in each cycle, modifying thermodynamic conditions compared to a standard heat death scenario. The presence of additional spatial dimensions or variations in fundamental constants offers alternative end states. String theory predicts extra dimensions beyond the familiar 3 of space and 1 of time. Changes in the compactification of these dimensions could reorganize energy and matter on a cosmic scale, potentially creating regions with different local physical parameters. These transformations are consistent with theoretical models in a multiverse context. The Big Rip and vacuum decay scenarios have implications for bound structures. In the Big Rip, atomic nuclei are predicted to be torn apart when the expansion rate reaches critical values, estimated to occur when the scale factor diverges in less than 10 to the power of 26 years. In vacuum decay, the bubble of true vacuum alters the laws of physics, rendering traditional bonds between particles irrelevant. Cosmic string interactions present another possible end state. Cosmic strings are hypothetical one-dimensional defects in spacetime, possibly formed during phase transitions in the early universe. If they exist, strings could stretch across billions of light-years, storing significant energy. Collisions or oscillations of these strings could release bursts of energy sufficient to perturb large-scale structures or trigger vacuum decay events. No conclusive evidence for cosmic strings has been found. Black holes may influence alternative end states. Hawking radiation predicts the evaporation of all black holes over timescales up to 10 to the power of 100 years. Some theoretical models suggest that quantum gravitational effects could form stable Planck mass remnants instead of complete evaporation. These remnants could concentrate energy locally, but would not significantly alter the overall expansion or thermodynamic evolution of the universe. Magnetic monopoles, if they exist, could influence long-term cosmic evolution. These hypothetical particles, predicted in some grand unified theories, could interact in ways that delay or modify processes such as baryon decay or vacuum transitions. Searches in terrestrial detectors like Super Kamiokande have not found monopoles, but their theoretical properties suggest that a surviving monopole could catalyze rare particle interactions billions or trillions of years into the future. A particularly noted alternative involves phase transitions in dark energy. If dark energy behaves like a metastable fluid, sudden shifts could lead to temporary contractions or expansions in localized regions. Some models predict that small pockets could experience temporary collapse, creating high-density zones in an otherwise low-density universe. These zones could generate new particle production, rare fusion events, or isolated gravitational collapse, while the broader universe continues expanding. Finally, a combination of alternative scenarios may occur. The universe could experience vacuum decay in some regions, while other regions undergo big rip-like expansion. Quantum tunneling could create isolated patches with different physical constants. The final behavior depends on parameters such as the behavior of dark energy, the stability of the Higgs vacuum, the existence of exotic particles, and the structure of spacetime at the quantum level. Cosmic evolution is influenced by initial conditions and fundamental constants. Physical models predict outcomes such as heat death, big rip, big crunch, or vacuum decay, each of which can be analyzed using current observational data and theoretical frameworks. The challenge for cosmologists is to constrain these possibilities. Observations of type Ia supernovae, baryon acoustic oscillations, the cosmic microwave background, and high-energy particle experiments refine our understanding of dark energy and fundamental constant. Experiments at CERN and long-term neutrino observatories contribute to measurements that could indicate whether vacuum decay is plausible. Indirect evidence, such as the distribution of galaxy clusters or the behavior of extreme black holes, also provides constraints on these outcomes. Alternative end states are influenced by dark energy, quantum fields, exotic particles, and cosmic defects. Observational and theoretical studies aim to refine the probabilities of scenarios such as heat death, big rip, big crunch, or vacuum decay. The ultimate outcome depends on parameters that are not yet fully constrained. Vacuum decay as a real physical event. In the landscape of cosmic futures, few events are as dramatic and irreversible as vacuum decay. Unlike the slow drift of heat death or the gradual stretching of a big rip, vacuum decay represents a sudden, universe-wide transformation triggered by the fundamental nature of space itself. The concept arises from quantum field theory, which treats empty space not as nothingness, but as a seething medium with potential energy stored in its vacuum state. If our current vacuum is metastable rather than the lowest possible energy configuration, there exists the possibility that a quantum fluctuation could trigger a transition to a lower energy true vacuum, reshaping the entire universe in an instant. Experimental data suggests that our vacuum may be metastable. The Higgs boson, discovered at the Large Hadron Collider in 2012 with a mass of 125.1 GeV, and the top quark, measured at 172.76 GeV, influence the stability of the Higgs potential. Calculations indicate that these values place the universe in a balance. While the vacuum is stable on human and stellar timescales, over cosmological durations it could spontaneously collapse. Statistical models estimate that the probability of vacuum decay occurring within the next billion years is extremely low. The mechanics of vacuum decay involve the nucleation of a bubble of true vacuum. Within this bubble, the energy density is lower than in our current vacuum, meaning that the laws of physics, the constants of nature, and even particle masses could differ drastically. The bubble is not stationary. It expands at speeds approaching that of light, consuming everything in its path. For an observer, the transition is effectively instantaneous. No star, planet, or black hole could resist the transformation because the underlying fabric of space-time and the forces governing matter are altered at a fundamental level. Cosmologists calculate the expansion speed of a vacuum decay bubble using quantum tunneling models. Early estimates by Sidney Coleman and Frank DeLucia suggest that once a bubble forms, it would expand at a rate indistinguishable from the speed of light in a vacuum, roughly 299,792 kilometers per second. Within minutes, the propagating bubble could encompass distances comparable to the observable universe, rearranging particles according to the new vacuum parameters. As the vacuum shifts from a metastable to a true state, the energy difference per cubic meter could rival or exceed the binding energies of atomic nuclei. The alteration of space-time geometry could affect black holes, and stellar remnants such as neutron stars or white dwarfs would be disrupted. The process occurs at the subatomic level and is governed by quantum laws. Observational evidence for the universe's metastable potential comes indirectly. Precise measurements of the cosmic microwave background, galaxy clustering, and high-energy particle interactions all provide constraints on the fundamental constants that determine vacuum stability. Experiments like the ATLAS and CMS detectors at CERN measure Higgs interactions with unprecedented precision, narrowing the possible configurations for the Higgs potential. Future facilities, such as the proposed Future Circular Collider, aim to improve mass measurements of heavy particles by a factor of 10, which could refine predictions for the likelihood of vacuum decay over the next 10 to the power of 100 years. The geometry of vacuum decay provides insights into space-time changes. The bubble's interior, governed by the true vacuum, may have different rules for curvature. Relativity suggests such a transition could alter light paths, gravitational interactions, and the speed at which information propagates. Simulations show that the boundary between metastable and true vacuum is an energetic, high-gradient region, releasing radiation and potentially producing exotic particles during the transition. Cosmic inflation, the exponential expansion of space in the early universe, shares parallels with vacuum decay. During inflation, a high-energy false vacuum drove rapid expansion, later decaying into the true vacuum and releasing energy that formed matter and radiation. Studying inflationary physics helps cosmologists understand bubble nucleation rates, expansion dynamics, and the interplay between quantum fields and space-time curvature. Even in a universe dominated by dark energy, vacuum decay could occur. Observations of Type Ia supernovae, large-scale galaxy surveys, and the cosmic microwave background confirm that dark energy density is small, roughly 6.9, 1 times 10 to the power of negative 30 grams per cubic centimeter, but uniform. In standard LCDM models, this causes eternal acceleration, pulling galaxies beyond observable reach. If a vacuum bubble forms, its expansion rate exceeds the accelerated expansion of the universe. The temporal scale of vacuum decay is unpredictable. Calculations of bubble nucleation probability suggest that the median expected time could be as long as 10 to the power of 100 years, but these estimates are statistical and do not guarantee when decay will occur. The stochastic nature of quantum tunneling allows for spontaneous vacuum transitions at any time. If vacuum decay occurs, baryons, photons, neutrinos, and black holes would be rearranged according to the new vacuum parameters. The transition is not governed by conventional thermal processes, and the resulting spacetime is defined by the constants of the true vacuum. Unlike heat death or the Big Rip, the energy distribution changes abruptly. Some models suggest that multiple vacuum bubbles could form simultaneously in distant regions, creating a fractal pattern of transitions. In a multiverse scenario, regions outside a given bubble may retain their original vacuum or have undergone different transitions, resulting in areas with varied physical constants. Finally, vacuum decay illustrates the interplay between empirical measurement and theoretical prediction in modern physics. While no observer can witness a decay event in real time due to its instantaneous nature, experiments in particle physics, astrophysics, and cosmology provide critical constraints. The observed Higgs and top quark masses, the cosmic microwave background temperature of 2.7255 Kelvin, and the distribution of galaxies all inform models of vacuum stability. By refining these measurements, scientists can estimate the likelihood of spontaneous vacuum transitions, explore the dynamics of bubble propagation, and assess the potential risks posed by metastable physics, even if the relevant timescales far exceed the current age of the universe. What comes after complete cosmic dissolution? Once the universe reaches the limits of its lifespan after heat death, black hole evaporation, and catastrophic events like vacuum decay, it enters a state of near-total dissolution. Ordinary matter has vanished. Black holes have radiated away into Hawking radiation, and the cosmos contains only ultra-low energy photons, relic neutrinos, and possibly a sparse population of long-lived, weakly interacting particles such as protons, if stable beyond predicted decay rates, or hypothetical particles like axions. Temperatures approach absolute zero around 10 to the power of negative 30 Kelvin or less, with negligible thermodynamic gradients. Quantum fluctuations remain a central feature of this final era. In the vacuum, particles and antiparticles can spontaneously form and annihilate in intervals on the order of 10 to the power of negative 21 seconds or shorter. Although the energy in each event is minuscule over vast cosmic volumes and durations, rare interactions may occur. Virtual particle pairs, including electrons and positrons or neutrino-antineutrino pairs, continue to emerge, constrained by the vacuum energy density estimated at 6.91 times 10 to the power of negative 30 grams per cubic centimeter from dark energy measurements. Residual radiation forms another key aspect of the post-dissolution cosmos. The photon bath left behind from black hole evaporation, including Hawking radiation from the most massive black holes, may be incredibly sparse, with densities far below 1 photon per cubic kilometer. The energy of each photon is correspondingly low, often well below 10 to the power of negative 30 electron volts, making detection impossible with any foreseeable technology. Relic neutrinos, once numbering around 340 per cubic centimeter, are now similarly diluted, traveling vast stretches of space with almost no interaction. The universe resembles an immense, nearly perfect void, where energy is uniform, and conventional physics provides few opportunities for complex processes to occur. Theoretical physics predicts that spacetime may still host phenomena. Gravitational waves, weakened by cosmological expansion, persist as perturbations in the spacetime metric. Their amplitudes are minuscule and may originate from mergers of black holes or collisions of stellar remnants billions of years ago. Exotic particle candidates may play a role in the long-term evolution of this empty universe. Axions, hypothetical particles proposed to resolve the strong CP problem in quantum chromodynamics, could form dense Bose-Einstein condensates under extreme conditions. Axion clouds might cluster gravitationally, creating minuscule structures with negligible energy compared to a star or galaxy. Likewise, weakly interacting massive particles, or WIMPs, if stable, could aggregate over time, forming microscopic clumps of dark matter that drift through the emptiness. The fabric of space-time itself may be susceptible to deformation or fragmentation. Over timescales far exceeding 10 to the power of 100 years, cosmic expansion continues to stretch distances, diluting any remaining energy density and effectively isolating regions of space from each other. Event horizons, shaped not by black holes, but by the accelerated expansion due to dark energy, grow ever larger, creating causally disconnected patches of the universe. In this context, quantum fluctuations could potentially produce tiny, self-contained pocket universes through mechanisms analogous to inflationary bubble formation. These nascent regions would be minuscule initially, but they may expand independently, obeying different local physical constants if the vacuum energy density fluctuates slightly during nucleation. Entropy in this universe reaches a theoretical maximum, estimated at 10 to the power of 123 K, B, with energy uniformly distributed. No gradients exist to perform work, preventing the formation of stars, galaxies, or other macroscopic structures. Some models calculate that rare quantum tunneling events could create temporary pockets of lower entropy, producing localized, short-lived energy gradients. Even after the end of all familiar matter, the universe may host a background of long-lived particles predicted by extensions of the Standard Model. Neutrinos, as mentioned, remain pervasive due to their extremely weak interaction cross-sections. Hypothetical particles like sterile neutrinos or gravitinos, with lifetimes approaching or exceeding 10 to the power of 100 years, may persist, drifting across the universe without decay. The distribution of these particles could be nearly uniform, forming a tenuous soup in which spacetime is filled with faintly interacting components, providing a residual texture to an otherwise homogeneous vacuum. With galaxies gone, stars extinguished, and black holes evaporated, conventional reference points for measurement or interaction disappear. Only fundamental quantum fields remain active. Fluctuations in fields such as gravitational waves, photon interactions, or rare particle decays continue according to quantum mechanics. Some theoretical models calculate that quantum fluctuations in vacuum energy could produce local density perturbations, potentially forming new structures over timescales exceeding 10 to the power of 1,000 years. These calculations are based on statistical probabilities of vacuum fluctuations, without asserting deterministic outcomes. If vacuum states differ across disconnected regions of space-time, some patches may undergo local decay or nucleation independently. Multiverse models use constraints from inflationary theory, the Higgs potential, and observations of dark energy to simulate different vacuum behaviors across regions. Even at these extremes, the constants of nature continue to govern potential interactions. Fine structure constants, gravitational couplings, and dark energy density define the behavior of particles and fields. Fluctuations in these parameters can alter the likelihood of particle interactions, bubble nucleation, or temporary entropy gradients. Simulations use these parameters to model possible outcomes in the ultimate dissolution of the universe. Finally, understanding the aftermath of complete cosmic dissolution illuminates the universality of physics across unimaginable scales. From the formation of the first atoms to the evaporation of supermassive black holes, and now to a universe dominated by faint particles and quantum fluctuations, the same fundamental forces continue to operate. This emphasizes the persistence of physical law and the subtle potential for activity, however improbable, long after traditional structures have disappeared. It demonstrates that even in a cosmos approaching absolute zero, the seeds of possible futures remain encoded in the fabric of space-time, energy, and quantum fields, offering a scientifically grounded vision of what lies beyond the ultimate cosmic end.